Thank you, Parkavi. I'll start by going through how solar energy actually functions. The basis of solar energy is converting sunlight into electrical energy. However, most of this energy is actually converted to heat due to inefficiencies. The underlying concepts rely on semiconductor physics with the p-n junction in particular. This is a p-n junction. A p-n junction is composed of a positively doped region that is rich in holes and a negatively doped region that is rich in electrons. Due to this, diffusion occurs where electrons move towards the p-type and holes to the n-type. A depletion region is formed through this as repulsion from light charges and diffusion balance out. This results in positive ions in the n-type and negative ions in the p-type. An electric field is formed, and when a photon hits an electron to create an electron pair, the pair will then move in different directions due to the intrinsic electric field resulting in current. A few factors affect efficiency in a solar cell. These will be band gap absorption, electron-hole pair formation, and electron diffusion losses. The band gap dictates the lowest energy that a photon can be to be absorbed. An important part of this is that no matter how high the band gap is, the amount of energy that the current conducting electron will have is still the minimum energy, which will be the band gap. This essentially means that a lot of energy is wasted. To balance this band gap, it is difficult. The ideal is around 1.34 eV. Something else will be absorption. If we cannot absorb a photon, it is impossible to convert the energy. Therefore, higher absorption will result in greater efficiency. The electron-hole pair formation mechanism is also important. Most methods like p-n junction only form one photon with only form one electron from a photon. However, certain nanomaterials may be able to generate multiple excitons from one photon. The last thing is electron diffusion losses. When an electron moves, it will lose energy, and minimizing this energy loss will increase efficiency. Next thing that I will be talking about is nanowires and their applications in solar cells. Nanowires are two-dimensional nanomaterials with their length being indeterminate. Solar cells are generally in vertical configurations due to the increased efficiency over horizontal geometry, and there are two main ways of constructing nanowire cells: axially and radially. In radial, the p-n junction is along the edge of the wire. For axial though, it is in the middle of the wire. In general, most semiconductors can be used for nanowire solar cells, from elementary semiconductors like silicon to compound semiconductors like gallium nitride and indium phosphate. 3-5 compound semiconductors are generally more efficient than others. Radial geometry is also theoretically more efficient as it minimizes carrier movement losses as compared to in the other configuration. Despite that, the axial geometry is actually still more popular among researchers due to ease of fabrication and large dopant concentrations required by radial geometry for efficiency. The band gap of the solar cell can also be tuned by simply altering the geometry of the nanowires. By changing diameter, we may be able to increase or decrease the band gap of this particular cell. In general, by increasing the nanowire's length, the nanowire solar cell will be more efficient. However, this effect does have a limit where it stops to occur. So why are nanowire solar cells more efficient than something like a silicon well? Well, it is primarily due to enhanced light absorption. Nanowires, if tapered, which are called nanocones, will improve light absorption greatly. Instead of discrete points where refractive index changes from one medium to another, nanocones create a gradient in refractive index. This captures light far more effectively. In addition, resonance is also present, which will also improve light absorption. Something else will be greater light scattering. By scattering light more than the natural material would, essentially light will spend more time in the material. By spending more time, it will have a longer apparent path, which results in a higher probability of the photon interacting with an electron and creating an exciton. All of these effects result in the graph shown, where nanocones are far more absorptive than other materials. There are also other things that make nanowire solar cells more efficient in general. the exciton formation is more efficient. This is due to reduced carrier relaxation, which is influenced by quantum mechanical effects like quantum confinement. Additionally, charge separation may use other mechanisms like LUMO and HOMO interactions. Charge transport is also more efficient. Band conduction is present, which makes it so that the electrons move more quickly and spend less time with diffusion-based movement, which is less efficient. In theory, nanowire solar cells could be cheaper. This is due to the lowered material requirements both in quantity and quality of the materials. Now I'll be moving on to the fabrication and limitations of nanowire solar cells. To create these cells, standard nanowire fabrication techniques like metal oxide vapor phase epitaxy (MOVPE), vapor liquid solid (VLS), vapor solid, and others are all used. Things like spontaneous growth, chemical etching, CVD, template-based synthesis, and lithography can be used with germanium as a common growth substrate. Electron beam lithography is typically used for patterning of the substrate. This is required for high performance. There are also some limitations to nanowire solar cells. They primarily improve light absorption only and reduce carrier movement losses. But as they still rely on p-n junctions, they are limited to only producing one exciton per photon. As a result, the charge output per photon remains restricted, which caps efficiency gains. There are also fabrication difficulties which would slow down development, like growth techniques offering limited fine control of dopant concentration and the p-n junctions characteristics. Finally, recombination on the surface is also frequent and also leads to lower efficiency. Now, I'll be passing the time over to Zheng Shen.